Hi everyone, welcome to my channel. Above Longtan Reservoir, every movement begins with exposure, precision, and disciplined control.
High-altitude cable cranes maneuver massive structural steel components with millimetric precision.
The first challenge was aligning a 600-meter crossing between two steep mountain walls.
At this height, tiny connection errors could multiply across the unfinished arch.
Before closure, both advancing halves had to meet at one exact crown position. To understand the bridge, return to the untouched reservoir corridor before construction began. Engineers first mapped fractures and weathered rock where the arch would enter the mountains. Core samples revealed whether each springing zone could carry immense compressive forces.
Rock quality analysis determined the precise anchoring depth for the arch foundations. Survey teams on opposite shores fixed one shared axis across the water. The selected solution used twin-deck type steel-reinforced concrete arch ribs. Inside each stiff skeleton, 4 steel chord tubes formed the temporary load-carrying frame.
Construction could not start until machines carved controlled access into the mountain.
The haul road became the supply artery, linking workshops, foundations, and both work fronts. Purpose-built jigs kept every fabricated segment within the geometry required for closure. Parallel work fronts allowed both shores to advance toward the reservoir together.
Controlled blasting prepared strong rock, without turning excavation into an uncontrolled event.
Simultaneous operations on opposite cliffs maintained structural and logistical balance.
Controlled blasting prepared strong rock, anchoring the springing blocks.
Controlled blasting prepared strong rock without turning excavation into an uncontrolled event.
Anchors tied the springing foundations directly into competent bedrock.
Reinforcement and embedded steel would transfer arch compression safely into each foundation block.
Heavy formwork shuttering enclosed each massive concrete lift. Cooling and curing controlled heat inside the newly placed mass concrete.
Opposite springing repeated the sequence while preserving its own mountain geometry.
With both springings formed, the permanent arch steel had not yet risen above them. Approach foundations were built separately to carry the roadway toward the main arch.
Approach foundations were anchored into stable rock to support approach spans. Crews poured approach piers to bridge the gap between mountain tunnels and the arch. Different pier heights showed genuine progress, not an instant jump to completion. Temporary tower foundations carried the cable crane system that would span the reservoir. Steel chord tubes were fabricated off-site and checked for exact tolerances. Plates and diagonal braces turned individual tubes into a rigid arch truss segment. Carrying cables created an aerial transport path between the two mountain work fronts. A no-load test checked travel, alignment, braking, and control before lifting steel. Trial assembly exposed fit-up errors, while corrections were still possible on the ground. Only after towers, anchors, hoists, and buckle stays were ready could erection begin. Barges carried finished segments through the reservoir to the cable crane pickup zone. Multi-point rigging controlled the segment without placing workers beneath the suspended load. The first lift transformed months of preparation into the beginning of the arch.
Hydraulic tools seated the first segment precisely into its embedded springing connection. Heavy pin connections locked the segment securely onto the springing block. Load transferred gradually from the crane into the springing and temporary stays.
The second arrival began a repeatable cycle of transport, lift, connection, and restraint. Each added segment required another stay level to control the longer cantilever. Three connected segments formed a short cantilever, still far from the reservoir center.
Balanced erection began when the opposite shore received its first segment.
After every connection, surveyors checked vertical and lateral movement at the cantilever tip.
Dawn measurements corrected for thermal movement before the next critical lift.
A controlled aerial rotation matched the segment to the changing arch curvature.
Temporary guides brought 4 cord ends into alignment high above the water. Buckle stays accepted the segment load before the crane was released.
The twin skeletons remained separate, parallel ribs joined by transverse stability members. Transverse cross braces tied the twin ribs together for lateral wind stability. Near quarter span, the growing cantilevers still depended on cables and temporary stays.
Scaffold platforms provided safe working access at the cantilever tips.
When wind exceeded the operating window, lifting stopped and the load returned to safety.
At mid-erection, the intended arch curve finally became visible across the reservoir.
Near the crown, every joint demanded tighter alignment and controlled bolt sequencing. The two arch tips approached one another, but the final gap remained deliberately open.
Engineers tuned stay forces until both tips reached the required elevation and position. The closure segment entered the center gap with only a narrow, controlled clearance.
Hydraulic adjustment reduced the remaining error to the millimeter scale. The final connection converted two cantilevers into one continuous arch skeleton. Stay forces were then redistributed gradually into the newly continuous structural system.
Ports, vents, and pipelines prepared the hollow steel chords for concrete filling.
Pressure and vent response tracked the rising concrete inside each concealed cord tube.
Concrete reaching the crown vent confirmed a complete fill path before sealing. Filling progressed between the twin ribs in a sequence designed to maintain balance. External reinforcement prepared the steel skeleton to become a composite concrete arch. The encasement advanced through 3 rings, 6 segments, and coordinated work fronts. Before each upper pour, inspectors verified cover, reinforcement, and embedded components. Symmetrical pours controlled stress, while the concrete shell developed or reveloped around the skeleton. Curing protected strength development and limited temperature gradients through the new concrete. The twin concrete arch ribs were complete, but the roadway still did not exist. Pre-stressed T-beams were cast in batches before delivery to the erection front. Reinforcement and drainage details were installed before the structural deck slab was poured.
The final wearing course produced an even roadway, without burying movement joints. The final view reveals the full arch, a mountain barrier transformed into connection.